So this, I think, will probably be the last. We'll probably finish the material, my material, in this lecture. And there might be one extra example or something to start the next lecture. Anyway, and then in the final 2 weeks, we'll switch the focus to doing revision activities and looking at some past paper solutions and revisiting any parts of the course on my half or Stephen's half that you would like. And I'll also be making available some solutions to some past exam papers. So the plan is to release the solutions to the last 2 years' worth of exam questions. So I just have to gather those. I'll be putting those up on Moodle very shortly. Well, you're still better off, of course, giving all these things a decent try yourself first, rather than just kind of going into the solution straight away. Okay. So, as far as Fourier series are concerned, we've just got this one last topic to look at, and we begin with a bit of nonsense, which is always good. And so the thing we're going to discuss is what's causing this nonsense. So the nonsense or contradiction, what we're going to do is we're going to return to the Fourier series for the function f of x equals x, which I believe we got that one. Yeah, illustrated here. Some of the early partial sums of it illustrated here. So the red function is, of course, the function f of x equals x on the interval minus pi to pi. And that the blue curve is the curve, the Fourier series just with the first 10 terms included. Of course, as you bump up the number of terms each time, you get better and better approximation of the original function by the Fourier series. If you're away from the ends, you've got quite good approximation. The blue function is almost entirely absorbed into the thick red band of the red graph. But still, at the end point, something funny is going on. This is what we refer to as the Gibbs phenomenon. Because, see, the Fourier series, remember, which is just that combination of sine functions, that's defined for all values of x. But the Fourier series, since it's built up out of the sine functions, is periodic. So you can see what it's doing here. It's at the top of the interval, when it gets to x equals pi, it's returned to 0 already. And that's where it started from at x equals minus pi. So if you extended the range of this plot out, you would see the Fourier series. I can probably do that just in the code. You see the Fourier series is periodic. If I do minus 7 times pi, 7 times pi there. You get the good idea there. This interval here, this small interval in the middle here, is the minus pi to pi interval. The Fourier series approximates the function over that interval. But extended across the rest of the interval, of course, the Fourier series just repeats that behavior that it did in minus pi to pi in a periodic fashion. All the time, okay? Because it's a naturally periodic thing. Really, the function being approximated here is what's called the sawtooth wave, the basic sawtooth wave, which shows a slow increase in the signal, then a severe drop, then a slow increase and a severe drop. When the Fourier series gets close to these points where it has to make the sudden drop, this is called the Gibbs phenomenon, where it starts to wobble about a bit. You know, it has good, quite tight approximation to the required values here, but then it starts to wobble. And this we likened to the fact if you're driving a fast car or cycling very fast. If you want to do a severe turn to the right, say, you be mindful of what you're doing next time you're on a bike. If you do a sudden turn to the right, you often precede it by veering out slightly to the left. And in beginning that turning behavior early on allows you to make a severe turn, which you wouldn't normally be able to do. But there's also something funny going on around this behavior. So what this example starts with is it takes this Fourier series. So this equation here, the infinite sum, is that blue Fourier series that we were just looking at. The blue graph we were just looking at was some finite initial part of this first 10 terms, whatever. But that's the Fourier series there. And if you just expand out the sum, you can see here you've got one sine function for every integer, and the coefficient is this alternating series, the alternating sequence of the reciprocals of the integers. Now, what we're going to do is suppose we could just take the derivative of both sides. Okay? So the derivative of the left-hand side is, well, the derivative of x is just 1, the derivative with respect to x. And on the right-hand side, you see a linear combination of all these sine functions. Well, let's just go ahead and differentiate each one and take the corresponding linear combination of the individual derivatives. So, derivative of sine is cosine, but there's a multiple of x, so you'd have a factor of 2 on the outside, so that's going to cancel the coefficient. You get this series on the right. 1 is equal to 2 times that combination of cosines. However, if you want to test out, if you just want to just inspect this a little bit, and we inspect it by just evaluating it at x equals 0, well, the left-hand side is just a constant, so it just has the value 1. On the right-hand side, you're evaluating each of the cosine functions at 0. But of course, cosine of 0 is just 1. So on the right-hand side, you've got 1, minus 1, plus 1, minus 1, plus 1, minus 1, plus 1, etc. So you've got this alternating series, of 1s and minus 1s. And that we claim is the nonsense. Because it's trying to say that 1 is 2 times this value here. But 1 minus 1 plus, this is a non-convergent series, okay? You don't have a single real value on the right-hand side. You've got a divergent series. So something has gone a bit wrong. What's gone a bit wrong is when we did that operation of differentiating both sides, we assumed that we were justified in doing this, that taking the derivative of the right-hand side, remember the right-hand side was this infinite combination of sine functions. We assumed that to take its derivative, we could just take the sum of the individual derivatives. But you cannot always operate that principle, okay? You certainly can. Now, okay, we shouldn't be too hard on ourselves, because this looks kind of good. It looks kind of reasonable. After all, we know that the derivative behaves like this on finite sums. If you take the derivative of a function f plus a function g, you know, and I encourage you to express it as such, that the operation of differentiation is linear. So if you take the derivative of a sum, it's equal to the sum of the derivatives. And that's certainly true for if you're differentiating a function f plus a function g. The derivative is the derivative of f plus the derivative of g. And the fact that it holds for 2 functions, if you extend it, you can reapply it, use associativity and stuff. You also get that it holds for any finite sum. And if you have like 5 functions added up here, you want to take its derivative, you can take the derivative of each one individually and add the 5 results together. And that's perfectly correct. Nothing wrong with it. It's the expected behavior, and it's the normal calculation tool that we use. But the problem is when you make that extra leap to assuming that you can do that for infinite sums. So infinite sums are a tricky beast. because they don't always give finite values. They don't always converge. And that's bad enough for infinite sums of numbers. If you talk about infinite sums of functions, which we often do, they are even trickier. You can talk about, so what we're going to be considering here is talking about the concept of having a sequence of functions, Fn, converging to a limit function. So this is a sequence of functions. Converging to a limit function. As n goes to infinity. And the question here is, well, what exactly do we mean by this? And can this happen in, does this always happen in the same way, or are there many different types of convergence for sequences of functions to limit functions? Okay. Well, it turns out there is, and there's at least two main kinds that you might consider. And this is linked to whether or not this equation here in 3.30, so, put a note here beside it. I'm not asserting this. This is just a description of what we did in that previous example. So there's a question mark over this. Is this a reasonable thing to do? Well, this example shows not always, because you can get contradictions from it. But is this ever a legitimate thing to do? Well, often it can be a legitimate thing to do. And what it depends on is the nature of this convergence here. So that's what the next two theorems, theorems 3.6 and theorems 3.7 are about. But before we get to those, we need to give you a little bit of background about this idea of a sequence of functions converging to a limit function. So we'll do that now. So how can a sequence of functions Fn equals 1 to infinity, so you got function f1, a function f2, a function f3, converge to a limit function f. Well, there's at least two ways in which that might happen. Of course, in terms of the graphs, we've got this intuitive idea that, well, the sequence of functions converges to a limit function if as you look at the graphs of the limit functions, if they get closer and closer to the graph of, if you look at the graphs of the sequence functions, if they get closer and closer to the graph of the limit function. And that's exactly what we were looking at in the case of Fourier series. Okay, there's one of the partial sums, that blue function. It's kind of close to the red function. It's still a fair distance away from it. But as you include more and more, if you go further out along the sequence of partial sums of the Fourier series, you're getting a function that is a better and better approximation to the original function. It's closer and closer to the original graph. Of course, what we're seeing there, though, is that it's very close to it around here. It's still got a bit of a way to go around here, though. So that's already a clue to the fact that convergence for sequence of functions, but there might be a little bit more to it than first meets the eye. But it's not an incorrect idea that the sequence of functions converges to a limit function if the graphs of the sequence functions look like they're getting closer and closer to the graph of the limit function. There's nothing wildly wrong about that, but it's that vague statement hides a number of technicalities. Okay? So the first type of convergence we're going to talk about is pointwise convergence. And this would be, if you look at each point x in the domain of interest, okay, we'll talk in the context of Fourier series here. You can generalize this out to any kind of sequence of functions. But at each point, we have a sequence, not a sequence of functions, but a sequence of function values, fn of x, as n equals 1 to infinity. So initially we're regarding functions as things in their own right. So we have a sequence of functions that are converging to a limit function. But if we just focus in on one particular argument, x, in the domain, and just evaluate each of the limit of the sequence functions at that same x, then the sequence we're looking at is now no longer a sequence of functions, but a sequence of values of this function. So it's just a plain old sequence of real numbers, just like the things we studied last year in maths fundamentals. Okay? Just a plain sequence of numbers. If these sequences always converge to the corresponding we take this claimed limit function f and evaluate it at this particular point. If you always see these sequences of function values converging to that final value, then we say that fn converges to f as n goes to infinity pointwise. If you zoom in on one particular point in the domain, observe the sequence of function values, sequence of numbers. If you observe that sequence converging to the limit value f of x, and if that's always the case for all the relevant x's in the domain of the function, that's the definition of pointwise convergence. The sequence of functions converges to the limit function if the sequence of function values converges at each individual point. Okay, that seems kind of obvious. Surely that is how we would define convergence, and indeed it is. But this is a little bit, there's a lot of looseness, there's a lot of freedom here. Because all we ask for is that when you zero in on each point, you're then looking at a convergent sequence of numbers. It doesn't say anything about what rate the individual sequences converge at. So it could be that if you look at certain values of x in the domain, you see sequences of function values that converge very rapidly to the limiting value f of x. Okay? It's a very good convergence in that sense. Very quick, rapid convergence. Whereas at other points in the domain, it could be that the convergence is a lot slower. Right? Achingly slow. It takes ages and ages and ages for the sequence values fn of x for some particular values of x. It takes them ages to get anywhere close to f of x. Of course, in the long run, they are going to converge. Okay, so you could have this convergence of the individual sequences happening very fast in some locations and very slowly in others, which is exactly the kind of thing we see here. Okay, so this is the 81th sequence function, the blue graph. For these values of x in kind of the middle of the two half ranges, the convergence is extremely close already. But if you're close to the value 0, any of these points, the function is still deviating a lot away from the limiting values. Okay, so we see that happening here. So nothing said here about the different rates of convergence. They may be all converging rapidly at the same rate, or you may have all sorts of different behavior going on. Okay? But pointwise convergence does not make any reference to that. All it asks is that look at each point, you've got a convergent sequence of function values. It doesn't refer to how the rates go. And symbolically, this is defined as, this is going to remind you of maths fundamentals, are symbolic convergence statements. It says for every x in the domain, I'll just leave it like that for all x, for all epsilon, there exists some point n such that for all n bigger than or equal to n, the absolute value of fm of x minus f of x is strictly less than psi. Remember, this is how we define convergence. For any value of epsilon, there was some point, capital M. If you look at the locations beyond that, look at the sequence functions, so to speak, n. Just change that to an m. Look at the sequence functions after that point, then their values, or their value at x is within the distance epsilon of the limiting value f of x. And this can be done for any x. For all x, that's true. Okay. But there could be, for different values of x, you could have different points n at which this agreement is obtained for the same points inside. The other type of convergence that we might have is called uniform convergence. So already you can tell by the title that this might be a bit stronger, meaning a bit more restrictive. This is going to say a lot more than what is said here in the pointwise. Because what is not said in the pointwise is anything about how the different rates of convergence compare to one another. So this is where there is a bounded rate of convergence for all points in the domain. So it's not, so what we don't do is zero in on each separate point in the domain first. Symbolically, what we say is, well, for any degree of closeness, there exists some point such that for every m greater than or equal to capital M, and for every x, the absolute value of fm of x minus f of x is less than epsilon. So this is saying something, it's subtle in a way, but it's also quite glaring in a way, the different thing it's saying. So this says, first it says for every epsilon. So epsilon is like the degree of closeness. Okay, this is measuring, this is the bound on the difference in values between the limit function, the sequence function values and the limit function values. So whatever degree of closeness you care to specify, there is some point capital M, after which, so for every little m bigger than that, after which, at all points x in the domain, you see the distance between the sequence function value and the limit function value being less than that desired or specified degree of closeness. Now that's, in some ways that sounds very similar to what we just said in the pointwise convergence. And indeed, I've used exactly the same symbols to define it symbolically, but crucially, they're in a different order. So the universal quantification over x in the pointwise case and the existential quantification over m, they've swapped positions here. Now the exist m is coming first, and the for all x is coming afterwards. Now that makes all the difference, because this one says, well, at every location x, it's possible to find an m which has a certain property. But it's entirely possible there that at different values of x, you find different values of m that have the required property. So at some values of x, a pretty small capital M might work, but at other values of x, you might have to go to a gigantic value of capital M. But in this second statement, it's saying there exists an m which works for all x, which has a certain property for every value of x. So that's quite different. It's saying that there is one m, there's kind of like a universal m. Given an epsilon, there's a universal m that functions in this way for every value of x. Okay, so that's saying something quite different. Okay. It's like saying, for every person in the world, there exists a mother for that person. Yeah, every person has a mother. It's not true to say that there exists a mother who's a mother to all the people in the world. Might be a grand, some great grandmother if you go back far enough, maybe we're all from one individual we can be traced back to, but you're just talking about mother-child relationship. You can see the difference when you swap the existential and the universal quantifiers. For every person in the world, there exists a mother. But it's not the case that there exists a mother for every person in the world. Okay. So swapping existential and universal quantifiers makes all the difference. So this is called uniform convergence, this second part. If you look back to our plot here, this looks quite non-uniform, okay? Because if you specify a narrow band around the limiting value, for instance, the thickness of that red band, okay? So the red band has a thickness to it. If that thickness is your epsilon, okay? So you're asking for the sequence function values, the blue values, to be close to the limiting values by that amount, by that epsilon. So you're asking for the blue function values to be basically inside the red band, which most of the time they are there. But crucially, there are locations where they aren't. Okay? So there is no one capital M. There is no one value of this index slider. So this is the number of terms. So this is the number of terms brought into the Fourier series summation. So this number is like the capital M. No matter how large I make it, there will always be locations where the blue graph is straying outside the red band. Okay? Not just at the value 0 where it has to go through a half, but at points close to 0 on either side as well. Okay? So there is that observation kind of confirms that this is non-uniform convergence. It's going to take a long time to do the summations there because I have to go in very particularly efficient. Okay. So this degree of closeness, the width of that red band, is never achieved across the whole domain. if you just focus in on any one particular point, even one of these badly behaving points, if I just focus on this value of x, I increase that slider far enough, eventually the blue graph at this location will be within the red line. But at points a little bit closer to 0, it'll still be doing this wacky stuff. Okay? So this is non-uniform convergence. And from analysis, calculus if you like, in order to interchange differentiation and infinite summation, you need uniform convergence. So if the convergence is not uniform, you cannot be sure that you can interchange the order of these two operations. So if we return to the notes now. This theorem 3.6, which we're not going to prove, but we're just going to take the information from it, this gives you conditions for recognizing when the convergence will be uniform. Okay, so we can kind of recognize from inspecting the graph of that example with the square wave function that the convergence is not uniform. So theorem 3.6 gives us conditions under which it's asserted that the convergence will be uniform. And you can certainly, when you read theorem 3.6, you can understand why the square wave, the example of the graphs we've just been looking at, you can see why that breaks these conditions. So the conditions are that, first of all, the function you're examining, it has to be periodic of the same period. Okay, so it has to be the underlying function has to be periodic with period 2 pi. And crucially, in order for that periodic behavior to knit together nicely, it has to take the same value at both ends of the interval. Okay? So f of minus pi must be equal to f of pi. In addition, the function f has to be continuous on the interval. So its graph shouldn't be broken apart at certain points of discontinuity, like the graph of the square wave. And finally, in addition, not only does f have to be continuous, its derivative has to be continuous. So that rules out examples of functions like, so this function here is continuous. Its graph does not make any sudden jumps in value, but you can see here its derivative does make a sudden jump in value. Because the derivative of this function, if that function is f, I can draw in blue its derivative. See, it's increasing with a constant rate of increase all the way up to this point, and then immediately it changes to decreasing, so that some kind of negative. Okay. So while this green function f is continuous, its first derivative is not, because it's got this sharp point. And sharp isn't a technical term in mathematics, but smooth is. We do talk about smooth functions and smooth manifolds. So this is a non-smooth point, a point where the derivative of the function is not continuous. So if our function satisfies these conditions, periodic at period 2 pi. It takes the same value at either end of the interval. The function is continuous, and its first derivative, well, if its first derivative is continuous, it's going to satisfy this. Oh, so actually, sorry, that's piecewise continuous. Sorry, this still is piecewise continuous. This derivative, because it's 2 continuous pieces. But anyway, we can take this condition as saying that the first derivative can't be too wacky. It can have points of discontinuity in it, but it can't, it must be made up of a union of continuous pieces. But certainly if the first derivative is continuous itself, it certainly satisfies this. So under those circumstances, we've got what's called uniform convergence. And this is needed in order to state our final theorem, which is Parseval's theorem. Now, just as an introduction to Parseval's theorem, recall a simple situation in V3R, three-dimensional vector space, with standard basis E1, E2, E3. Any vector x from V3R can be written as a linear combination lambda 1 E1 plus lambda 2 E2 plus lambda 3 E3. Any vector can be written as a linear combination of the three basis vectors. And the norm of the vector, or let's talk about the square of the norm, which is equal to the dot product of the vector with itself. That is just the sum of the squares of the three coefficients there from the linear combination. And this holds because the standard basis E1, E2, E3 is an orthonormal basis. It's a basis. All the vectors are mutually orthogonal. Each one is orthogonal to all the others. And the normal bit means each one is norm 1. Each one is length 1. So this is a very nice setup to have a nice, well-behaved basis for the space. Orthonormal, mutually orthogonal vectors, all of the same length, all of standard length 1. Any vector x can be expressed as a linear combination because they're a basis. And the length of x, the square of the length of x, is the sum of the squares of the coefficients. Now, we've been stressing all the time that Fourier series, we should think of it in these linear algebra terms of having a vector space of functions, this infinite basis for the vector space, so these cosine functions or the sine functions, and that any function in the space can be expressed as an infinite linear combination of those basis functions. Well, Parseval's theorem gives us the equivalent thing to this in the setting of Fourier series. Okay. So I think you'll find the statement of theorem 3.7 a lot easier to appreciate because you've got this quite well-known, familiar scaffolding that you can map it onto. Okay. So if you look at the statement of theorem 3.7, now it does place conditions on the function. So we need the function, we need the Fourier series of the function to be converging uniformly to the limit function f. Okay? But as long as the Fourier series is converging uniformly to f, and the previous theorem gives us conditions on f that would guarantee that, then this integral here, but of course this integral here is more or less the square, the equivalent thing to the dot product of x with x. Because this is the inner product of the function with itself. So it's the integral over the interval of the square of the function f of x times f of x. Okay, so this integral on the left-hand side is it corresponds to the x dot x we just saw in the previous example. So this is the inner product of the function with itself, rescaled a little bit, 1/2 pi here. And basically what we have on the right-hand side is more or less the sum of the squares of the Fourier coefficients. Now remember, the constant coefficient in the Fourier series is 1/2 of this parameter a0. So the square of that is going to be 1/4 a0 squared. So there's just this messiness regarding the constant coefficient. And yeah, so we're not just taking the sum of the squares, but we're taking 1/2 of it. But then this is, it's kind of impossible to straighten out all these different scaling coefficients all over the place. But this is basically the dot product of the vector with itself equal to the sum of the squares of the coefficients from the linear combination, except expressed in the correct way in the setting of the vector space of these functions and their Fourier series. And if we know the Fourier series of a function, then Parseval's theorem can often give us some quite interesting consequences. Okay, so that's in that last example, example 3.9. But I don't want to rush this, so I think I'll make this the last thing I do at the start of my next lecture in Fourier series. This evening's one is going to be on, we're back to inner product, Stephen's half, back to the inner products now this evening. But this final example here shows you a nice example of applying Parseval's theorem to a certain Fourier series. Okay, because the idea here is the idea of this example is to obtain a value for this sum. And the reason the Fourier series helps you is this sum is the sum of the squares of the coefficients from the Fourier series. We've 1 or 2 coefficients at the front, but mainly all the coefficients from the Fourier series look like this quantity here, 4n squared minus 1. So Parseval's theorem, which tells you about the sum of the squares of the Fourier coefficients, we can use that to approach this sum. Parseval's theorem relates it to the inner product of the function with itself. That's going to be an integral of sine squared, which we can, as long as we can evaluate that integral, we'll be able to evaluate that infinite series. Okay, so we'll see that application at the beginning of next time, and then that should wrap up the Fourier series. Okay. Okay, so thanks for your attention. I'll see you a couple more times today for some linear algebra.